I'll be talking about our paper enforcing customizable consistency properties in software-defined networks. Joint work with Dongjin, Jason Croft, Matthew Caesar, and Brighten Godfrey. So the problem we are tackling here is network update problem. It asks how do I move my network from one configuration to another configuration. As networks are getting more and more dynamic, partly an effect of SDN, network changes can happen frequently due to a number of reasons, like control applications, changes in policies, changes in traffic load, or system upgrades. So even though the configurations could be correct, there's another challenge remains. How can we make sure all the intermediate states are also correct during transitions? As networks are becoming critical infrastructures and they are subject to attacks, we need a stronger notion of correctness, that is, correctness at every step. And in addition, we have to minimize the duration of network errors or performance drops, we need to react to network changes in a timely fashion. So correctness and efficiency. How can we achieve both? But the first question is, what is correctness in networks? We can understand that as the network behaviors comply with some desired properties, the range of such desired properties could be quite diverse. For example, some successful operations of some network may depend on a set of paths traversing a firewall, or classified hosts being unreachable from external domains, or simply loop freedom. So intuitively, the stronger a correctness property is, the longer the update process needs to take. What we can do is actually make use of this trade-off to customize correctness level for one special purpose for better efficiency. So to sum up, the question we want to answer here is it possible to efficiently construct a system that efficiently ensures that customizable correctness properties are maintained as the network evolves, as dynamics happen in networks? So let's first take a step back to look at existing solutions. Consistent updates is probably the closest one to ensure customizable, generalized consistency. It provides a relatively strong property called packet coherence, so it's sufficient to guarantee any property that is weaker than that. But at the same time, it sacrifices efficiency in terms of both update speed and switch memory cost. So DNSS was recently proposed to dynamically update network on top of a dependency graph of updates. It allows users to trade a correctness level for better efficiency, but to do so for different invariants, it requires writing a specific algorithm to generate such graphs. So with those three objectives previously mentioned in mind, we find existing solutions are not good enough. Ideally, what we want is the best of both worlds, the efficiency of simply immediately update network with no delay, and the safety of whatever correctness that is relevant to this network at hand. It would be great to have this magic box, but as a step towards that, to move closer to this ideal world, we have proposed our design in the context of SDN, Customizable Consistency Generator, CCG. So how does the technique work? Our philosophy behind the design is that synthesizing consistent updates for arbitrary policy is hard, but network verification on general properties is relatively easy, especially now that we have those real-time network data plane verifiers that is able to verify network snapshot against the very generic invariance within milliseconds. So. And in fact, as also occurs in domains outside of networking, there's a connection between synthesis and verification. Because a feasible update plan is one that which the relevant property is verifiable at every moment. So based on this insight, we reduce the problem into a series of verification problems through the following workflow. So inside the CCG, we have a network verifier. Like other network verifiers, it consists of a network model and a verification engine which checks the model against the supplied invariants. So network programmers can express their desired invariants as essentially functions of the model. So next, the CCG runs a Grady algorithm. As new update comes from the controller to CCG, it checks whether the network would satisfy the supplied invariance if the update were applied to the network. If the answer is yes, then the update is sent with no delay. Otherwise, it's buffered temporarily. And at each step, by that way, what I mean is some new update comes from controller or feedback from the network. CCG will check this buffer to see if any pending updates can be sent safely via repeated verifications. So let me work through an example. Suppose we have this network and want to make sure traffic comes into switch A can always reach switch B. Initially, A can reach B through CDE along the orange arrows. And we want to migrate the traffic to a new path AFGHB. So at least the 4 updates are necessary, as listed in the table. We need to modify rule at A and add rule at F to G, G to H, H to B. Suppose the updates comes from the controller to CCG in the order of 4, 3, 1, 2. As CCG gets 4, it checks its model, see if 4 were applied. It won't affect the old path. So A can still reach B, so 4 is safe to be sent to the network. And similarly, 3 can be sent with no delay. Now, 1 comes. CCG checks, see if 1 were issued, A would switch to the new path, but F won't be ready by then. There would be a black hole at F, so 1 has to be buffered temporarily. Now 2 comes. Passes verification and sent to network. This new event actually makes sending 1 safe now, so 1 is released. So in this way, CCG maintains the order among updates only when it's necessary with respect to the invariance of interest, and thus heuristically maximize update speed. However, this simplistic algorithm has 2 problems. So the first challenge lies in the verifier. Because existing data plan verifiers, real-time data plan verifiers assume that they always have a fully up-to-date network-wide view. That is, updates take effect as soon as they are issued, which is not correct. Since network is a distributed system, we cannot know when and in what order exactly the updates are applied. So, and the second challenge is about the Grady algorithm. It's a Grady algorithm. It may not produce the best update sequence, and even worse, it may get stuck with no updates installable without violating the invariant. So next, I will describe in detail how CCG addresses each of the challenges here, starting from the first one, network uncertainty. So because networks have to disseminate states among a bunch of distributed and probably asynchronous devices, from any observation point, even its SDN's controller, there might be a time period during which this point view of the network is different or, say, inconsistent from the actual network state. We refer to this time period as temporal network uncertainty, and we'll use uncertainty for short. So being unaware of this uncertainty may deviate the network behavior away from the desired ones, as I will show in this motivating example. So suppose we have these 2 switches, and initially switch A has a rule directing traffic to B. For some reason, we want to flip the traffic by issuing 2 instructions. First, remove the rule at A, and then insert a new rule on B to direct traffic to A. If the controller has no idea of this uncertainty, as after it sends out the first instruction, it thinks it's immediately applied to the network, so it updates, the controller updates its view as this. But at this moment, the actual network view could be either one of the views at the bottom of the screen. And after issuing rule 2, the controller again immediately updates its view as this. Now the network states could be any one of those 4 possible states. Suppose the operation of the second instruction indeed finishes earlier than the first one. a transit loop would occur in the network, and which can lead to packet losses. So to this problem, our answer is that we model this uncertainty explicitly. So to model network state can be naturally mapped into a graph with nodes representing devices and the links representing rules. Naively, to model uncertainty for every update, we need two graphs to represent the network behavior with and without the effect of the update until the controller is certain about its status. Suppose we have n update concurrently in flight from the controller to the network, then we need 2 to n graphs, which apparently is a state explosion. To address that, CCG models the behavior of the network as an uncertain folding graph, whose links are marked as certain or uncertain. If a link is uncertain, that means the controller has not have information about whether or not this corresponding rule the corresponding update is applied to the network or not. Otherwise, the link is marked as certain. The graph is maintained and updated over time. As for the details of that, please refer to our paper. We have also proved this, assuming all the updates are coming from the controller. Our model can accurately capture the network behavior from packets view. Even for those packets that's that have been passed by some rules currently not present in the network. So in this way, CCG collapse all the possible states into one graph. And using this graph model to do verification is fairly straightforward. By traversing the graph, we can answer, using some directed graph algorithms, we can answer queries such like if there's a path exists between a pair of nodes in a similar manner as some of the current verification tools like HSA or Veriflow. But during traversal of the graph, we have to take uncertainty into account, because while we're traversing an uncertain link, we need to keep track of the fact that downstream inferences lack certainty. For example, if we are at a node with no certain outgoing link, even though there might be multiple uncertain outgoing links available at this node, it's possible that packets got dropped there. So in this way, by traversing the graph once, CCG is able to reason about the network state in the presence of uncertainty and raise alarm or something like that to when it determines there's any possibility that the invariant is violated. A remaining question is about the performance of the verifier, because although compact, the model is still potentially larger than those of the existing verification tools because of this uncertainty awareness. Another reason is that as a subroutine of the scheduling procedure, our verification function is called much more frequently than those of when it's purely used for verification. For these reasons, substantial efforts went into optimization. But for the sake of time, please refer to our paper for the details and the macro benchmark results. So now let's move to the second challenge, the limitations of the Grady algorithm. Let me explain the problem through another example. Suppose now we have this network, and the invariance we want to ensure is packets come into A should always reach switch E. But before that, traverse firewall F. The initial path from A to E is A, B, F, D, E along the orange arrows. We want to migrate the traffic to a new path A, D, F, B, E along the blue arrows. So again, 4 updates are necessary as in the table. And suppose they are coming from the controller to CCG in the order 4, 3, 1, 2 again. As CCG gets 4, it checks the network's model. See, if 4 were applied, the rule B to E were added, the path will change to ABE. F is bypassed, so 4 has to be buffered. Now 3 comes. 3 would modify the rule at F. That would cause transit loop between F and B. 3 has to be buffered also. Now 1 comes, if 1 were issued, A will switch to the new path, resulting a path ADE. So F is bypassed again, so 1 has to be buffered. Now our last hope 2 comes. 2 would add a new route D to F that would result in a transit loop between D and F. So all the updates are buffered. The heuristic gets stuck. So our solution to this scenarios like this is we adopt a hybrid approach. Suppose the operator wants to ensure some property that can be guaranteed by an existing solution. By that, what I mean is given configurations that satisfy the desired property, this tool can move the network in a way that all the intermediate states also satisfy the property. Suppose such a solution can be specified and plugged in. So the stream of updates comes to CCG would first be handled by the heuristic still, as long as the policy is not violated. Anything violated policy will be put into the update queue temporarily until it reaches a point that the heuristic determines that I cannot proceed anymore. Then all the pending remaining updates will be fed into the fallback mechanism, the plug-in solution, to be transformed into a feasible sequence. And then the output will be handled proceed by the heuristic again to try to heuristically maximize the update parallelism. In this way, assuming the solutions exist, CCG can always guarantee feasible update sequence. So note here, even with fallback triggered, CCG still achieves better efficiency than using fallback alone to update the network because of 2 reasons. Reason 1 is that typically only a fraction of the transition is left to be handled by the fallback. And reason 2 is CCG only uses the fallback mechanism to translate the remaining updates. It doesn't necessarily need to pay the overhead of the fallback mechanism. For example, the waiting time between the 2 phase inconsistent updates. So, even better, we have, it turns out there's a fairly large scope of properties that, for that feasible update sequence orderings always exist, and the CCG's heuristic is guaranteed to find one. We focus on waypoint properties. A waypoint property tells you a set of waypoints that flows are required to traverse. Many common properties fall into this category. Examples include the connectivity, waypointing, access control, and service chaining, etc. So we have, in a paper, discovered and proved the condition that the waypoint property is guaranteed by the heuristic alone, and we refer to those properties as segment-independent property. Okay, so to put all the pieces together, we have this figure shows our overall approach. Our uncertainty-aware model will prepare a network model for the verification engine, and the verifier is responsible to produce verification results. Based on this result, CCG will use the heuristic together with a fallback mechanism when it's necessary to produce an efficient and correct update sequence. A key feature of CCG I want to emphasize here is it operates in a black box fashion. So, for example, it provides a very generic platform for general consistent correctness policies. For example, one can plug in different verification functions or different fallback mechanism. We have implemented a prototype of CCG and 2 fallback plugins based on consistent updates and so on, which is a tool that guarantees absence of packet loss. And through evaluation, we try to answer the question, is CCG able to speed up update while obeying properties including segment-independent and non-segment-independent properties? We have conducted evaluation through emulations and experiments on our SDN testbed, but here I will focus on emulation results. only. So first, the segment-independent properties. We using Mininet, we emulated factory topology with 5 core switches and 10 edge switches. Each edge switch is connected with 5 hosts. Shortest path and load balancing application is running in a Tox controller on top of a CCG. So at the beginning, we initialize each set of experiments with only one core switch enabled, and brought up the other 4 later. So the application would issue updates to even traffic across all available links. For simplicity, we refer to the delay between controller issuing update and the corresponding switch finishing updating, applying the update as switch controller delay. By adjusting the number of that, we mimicked both local and the wide area settings. For each set of experiments, we measure the completion time of each path, communication path, that is from host to host. So this figure shows the CDFs of 6 update mechanisms in local setting. We tested when the controller issued updates immediately to the network with no delay, which is optimal in terms of speed, and the CCG configured with connectivity invariant, which requires no loop and black hole from host to host, and CCG configured with an actual invariant, which requires packet traverse a specific middle hop before reaching its destination. And consistent updates, incremental consistent update, and variant of consistent update that trading time for better switch memory usage, and DNSs with a packet coherence invariant, which is the default algorithm introduced in the paper. So note here we used our own implementation of DNSs, and packet coherence is a pretty strong property. So it's not a full evaluation of DNSs approach, because one can implement their own special purpose algorithm for weaker properties and thus achieve better efficiency. So from the figure we can see CCG's curves, both of the curves are very close to optimal and much faster than consistent updates. One thing I forgot to mention that the application used in this set of experiments, we configured those at the same time as in Dennis's paper. By that, what I mean is rules are not overlapping. One rule can only match one flow. So we proved in the paper, in this scenario, in this topology and this application, both connectivity and waypointing properties are segment independent. So that means CCG never needs to trigger the heavyweight fallback mechanism, so it requires no additional memory cost in the switch. Here is the wide area setting result. So CCG saves even more time compared with consistent updates, but that's majorly due to the longer controller switch delay. We have also explored the scenarios when CCG does not, CCG's lightweight heuristic does not always guarantee us a correct update order. For this, we collected traces from a network with more than 200 layer 3 devices. During one day, we selected 10 of them, the strongly connected ones. During one day period, we took snapshots per hour and used the Mininet to perform transitions to between every 2 successive snapshots. So we, because the rules here are overlapping with each other with longest prefix match, as we explained in the paper, they are, even for black hole freedom and loop freedom, they are not segment independent. So that means CCG sometimes have to fall back to the heavyweight mechanism. So from this figure plotted the number of total rules in the network over time and in full transition windows. Most time the network is pretty stable, so there's a relatively small number of updates. More interesting case is the 2 middle windows. From 11 p.m. to 1 p.m., there's a huge burst of dynamics. So over 8,000 updates happened in each window. Even for this huge number, we can see, let us zoom in and see the number of updates have to be forced to fall back to the. In this case, the fallback mechanism is consistent updates. The number of updates have to be forced to fall back is quite small. It's less than 20 in this case, in this window. So on the figure, we can see those dots. They indicate the ending time of each update scheme in each window. From those dots, we can see the CCG's completing time is quite close. Overall completing time is quite close to the immediate update, which is optimal in speed. So the major takeaways in this figure is, first, the fallback is rarely triggered, and secondly, CCG can have comparable performance compared to immediate update scheme, but without any of the short-term network faults that the immediate updates would introduce. So to conclude, we introduced our system CCG, which can efficiently update network while obeying customizable network consistency properties. And there are a number of interesting ongoing work. We plan to study the generality of segment-independent properties and handle network initiative changes, test the CCG with more traces and compare it with Dennis's fully. So that's all. Thanks.
Okay, maybe we have time for one question.
Hi, Saeed from CMU. So very nice work. So my question is, what range of properties can be covered using your method? So if you think of, for example, reachability policies, things that HSA looks at, so is that something you consider? Or can we think of like firewall policies, stateful policies, that sort of forward and backward traffic should go to the same node?
Could you repeat your example?
Sorry?
Could you repeat your example again?
So my question is, what is the category of properties that could be covered using your method?
So basically, we are focusing the properties that can expressed in the form of the data plane graph, like reachability properties and access control, graph-based, topology-based properties.
So does it cover stateful processing like firewalls or proxies or intrusion prevention systems?
Yeah, yes, that's correct.
Okay. Let's thank the speaker.